Oh, that was such a good talk. I really enjoyed that. Let me
Yeah, and
get.
now you're up next. You're up next.
Yeah, no pressure.
So
This is
no
like,
pressure.
I'm afraid I'm not going to write a paper during this talk or magically make a bunch of Git pull requests. That's so sad. But God, that was so good. Right. Tell me when I should go, I guess.
Yeah. So what you can do is, I mean, you can explain to us exactly what are creative monads and about type level programming for dependence analysis. Go ahead.
Yeah, I will. All right, I'll just get started then, shall I? Right.
You can.
Hello, I'm Finbar, and today I'm going to talk to you about this joint work with Michael Gale on graded monads and type-level programming for dependence analysis. There's quite a lot going on in this title, so let's start off with a motivating example. Oh, gotta click. Here's a robot I found earlier, and what we're going to do is take its sensors, like this distance sensor, and its actuators, like this motor, and represent them as mutable memory cells, like I/O refs. So on this robot here, we have a distance sensor, which you can read from to get the value that's currently being detected by the distance sensor. Same with this light sensor. We have a pair of motors where you can write to them to set the speed. And we have this robot screen, which we're going to use as both an input and an output. You can write to it to set the value on the screen, and you can read from it to get the value that's currently shown on the screen. With that in mind, what we could do is define our robot's functionality as a collection of computations that read and write from these memory cells. So here, for all of these computations are represented by these arrows, where they go from the cells they're reading from to the cells they're writing to. So we have this remove error computation, which reads from the distance sensor. Maybe it removes some error or whatever, and writes that result to the robot screen for debugging. Then we've got this write to motor that reads the result that's stored in the robot screen and writes it to a motor. And then we have this hit if dark, which separately reads a light sensor and then maybe turns on the motor when it's dark enough and it's detecting an object in front of it. And on the right, we have two possible implementations for this. There are lots of implementations, but here are two of them. The first one, we sequence them with remove error, then write to motor, then hit if dark. And then with robot prime, we swap the first two. Now, here's our problem, and the main thing we're going to focus on in this talk. If we run robot prime here violates a data dependency because it ends up using an old value from robot screen. So by running it first, we get the old value, and then we update the value of robot screen with remove error afterwards, which is a problem. Ideally, we would like these values to be propagated through the network properly. This might be fine if these computations are being run like once every 30 times a second or whatever. But if we have a sensor that only updates every few seconds, then you get a real problem because that motor will be the wrong speed for a few seconds and could cause the robot to crash or do something similarly bad. Furthermore, we'd ideally like to not worry about sequencing these things at all. An example here is hit if dark, which could be run anywhere within the order of computations, but we still have to sequence it because that's just how I/O computations work. You have to write the order and give that order. So ideally, we'd like to solve this. One thing I should also mention is the fact that our sequencing error that we talked about, this remove error write to motor issue, is mainly caused because the types aren't specific enough. If we consider both of these definitions are well typed, because neither of them talk about the reads and writes that they're exactly doing. They just go, oh, there are some reads and writes. Trust me, this is all going to be great. So ideally, we would like some better types to represent these computations with, and then have some way of avoiding the sequencing. And we're going to do this in 3 steps. First, we're going to make the computation types more specific, as I said. So instead of having these I/O units, we're going to make them reflect exactly what reads and writes they do. This is the graded monad part of the talk, spoilers. The next thing we're going to do is take a look at these types and prevent dependency violation at compile time by using type families to order them. Then finally, we're going to take this compile time result, this new type that we've got that correctly orders the computations, and apply this result at runtime, which requires a few extra steps that we're going to briefly talk about. So, first section, make computation types more specific. As I said, we're going to look at how these computations are currently typed, and then introduce more specific types that detail these reads and writes. So here is an example implementation of write to motor, that one of the computations from the robot example we just showed, where we're essentially going to get the value from the screen and then immediately write that value to the motor rather than doing anything with it. This is a very simple implementation, but you could imagine more complex ones being here that like actually do something with the value. To do this, we're going to get the screen val by reading an IORef. For this talk, we're going to stick with IORefs. And we would really like it if this type reflected the fact that we read from the screen variable specifically. Similarly, for put motor, we're just going to write an IORef, and we'd really like it if that type reflects the fact that we wrote to motor. And then finally, we would like the type of the composition to reflect both of these things, so that we both read from screen and we write to motor. Fortunately, we have a neat solution for this in the form of graded monads, introduced to Haskell specifically by Orchard and Petracek back in 2014. Here's the existing definition for monads in Haskell, and we have a bit of a problem. If we wanted our computations to say somewhere in their type, oh, I do this read, and oh, I do this write. So let's say we wanted this first computation to have an m which says I read from this variable, and this m to say, oh, I write to this variable. We can't, because these m's have to be the same. But fortunately for us, graded monads solve this problem by introducing a type parameter that the monad, or by parameterizing this monad over a monoid. This monoid has a unit type, which represents the parameter of doing nothing. So our return operation now has this m unit a type to say, we don't actually do anything here, we just bring it into the monadic context. And then we have plus, which takes two parameters and combines them. So what we can say now is if we have some mfa where maybe f is reading from a variable, and then we have this a to mgb where g is, oh, I'm going to write to this variable. We can now combine them with this plus operation to say, oh, we do both of these things. They've been used in a variety of different contexts in the literature, like dealing with concurrency, avoiding deadlocks in concurrency, and making better reader monads that allow you to see exactly what's being read in them. But this is fairly new. This is a new application. This is the type that we use to encode our reads and writes, and therefore to encode the dependencies between computations. We add a parameter s, which represents the cells being read from and written to. So we represent these as a pair of type level sets. We're using a single parameter because that's what fits with graded monads in the literature. These are treated as type level lists of type of kind star, but morally we're going to be treating these as sets. And in the actual code provided in the paper and alongside the paper as an artifact, we use the type level sets library. This monad is accompanied with this run memory function that takes in the memory cells being used. So this is the value level representation of the cells in our sets, and gives us a computation out where we take in the things we're reading and writing, and then we read and write them. It's that easy. This is a graded monads. We provide the type family we provide unit and plus as follows, where unit is the pair of empty sets saying we don't read anything and we don't write anything, which makes sense. If we return, then we're not doing any memory, we're not actually accessing memory at all, so we have these two empty sets. And then we have plus, where we take the element-wise union of the two sets. So the combined computation does all of the reads of both computations, and the writes are the combination of the union of the two sets of writes. Final thing we need to do is we need something to put in that type level list. And what we do for that is we name memory locations rather than just using raw IORefs, which would have some problems because we want to look at we want to check uniqueness of types effectively. And if we say if we only use an IORef, then you're only allowed one IORef int, which is really bad. But we associate them with a symbol kind, which is a type level string that allows you to give our IORefs a name. So to give an example of that, we have input here, which is an IORef int, and then we turn it into a cell simply by associating it with a type level string. In this case, we've gone with input because that makes sense. You can do this either with an explicit type annotation or with a type application, which is lovely. And with that, we can now define our own read and write operations that do this properly and that successfully track our reads and writes. So we have read IO cell here, which takes in an IO cell with the name S and the type T and gives us a computation with that as its reads, no writes, and a thing of type T. And similarly for write IO cell, except we're storing it in the list of writes rather than the list of reads predictably. So with that, we can now rewrite our initial example. We have getScreenVal now successfully mentions the fact that it reads from screen, and we use read IO cell to confirm this. Put motor reflects that it writes to motor, and then we take the union together, and wow, that's exactly what we want. We now have computations that effectively represent the reads and writes that they do. So now we need to actually prevent this dependency violation, and this is where the type-level programming comes into it. We're going to build a dependency graph and word this as a graph problem. But first of all, we need to do a few extra little steps to make sure that everything, well, to lead up to that point. So first thing we want to do is talk about what our goal is for the rest of this section, for the rest of this talk. So what we want is, now we've got these better types, we can represent a group of computations as a H-list, a heterogeneous list. The definition is given on the bottom of the slide, but the main things you need to know are that this colon plus colon operator is list cons, H-nil is the empty H-list, and the resulting type corresponds to the types of its individual elements. So for example, remove error has the type disk to screen, hit if dark has the type light to golf, write to motor has the type screen to motor. Note that we're shortening the types here because otherwise the types are going to get very long, and that is an issue with using graded monads and using these kinds of type representations. We're combining these computations arbitrarily. We don't care about the order because the compiler is going to fix this for us. So as it says on the slide, we're going to use this type information to find a valid ordering for these that does not violate any of the dependencies. So step one, we need to determine the order of these computations more formally. So we need a type family that says this computation must run before this one. We use the notion of data dependencies from an old Bernstein paper. So for example here, write to legs has a dependency on remove error, since remove error writes to screen and write to legs reads from screen. So we need write to legs to run after remove error. This can be implemented as a fairly simple type family where we're just pattern matching on each of the components and then getting the intersect of the intersect of the cells written by one computation and the cells read by the other computation, and checking whether it's non-empty. That is there a cell shared by the two that forces a dependency to exist? And you can see that in work here. So we have MIO applied to MIO disk screen, MIO screen motor. There is a dependency. So this type family correctly shows us that this dependency exists. So what we're going to do now is generalize this, or not generalize this, apply this to all of our computations pairwise to build a dependency graph, where an edge on the dependency graph represents there being a dependency. So in this example, there is a dependency. Write to motor depends on remove error, but there are no other dependencies. So this is our resulting dependency graph. And with that, finding a valid ordering is simply just finding a topological sort of this graph, because that's what a topological sort does. So for the rest of this section, we need to talk about implementing these graphs and implementing topological sort. So we represent a type-level graph as an adjacency list, taking this mapping type, which is from the TypeLevel sets package, and we're going to map nodes, which are types, to their in edges and out edges, which are lists of types. As a result, we also get some nice type families like get in edges and get out edges that get these in and out edges for us. This is really cool for reasons that will come up in a couple slides' time. Now we have to take a brief detour before we can talk through our implementations, because because like in the Haskell paper, we use first-class type families by Chia. First-class families is a really cool trick for making type families partially applied, because regular type families are not allowed to be partially applied until unsaturated type families becomes more prevalent anyway. I'm very much looking forward to unsaturated type families. It's going to be great. These partially applied type families are simulated through data constructors, which can be partially applied. So for example, we have this non-empty intersect data constructor, which takes a list of kind k to a list of kind k to an exp bool. We'll get to exp in just a second. And then to define how that family is executed, we define a type instance of alpha list. So we're saying if we get a type non-empty intersects x is y, good news. This is how you implement. This is how you execute it and get a result out. So we should now talk about exp briefly. As was mentioned in the Haskell talk, exp is basically a trick to make sure that the type checker doesn't hate us. Data constructors can't have non-star kind as their return type, which is really irritating because there are lots of type families that we use which don't have kind star return types. So stuff like filter, for example, which would give us a list of kind k, we couldn't represent that as a data constructor. So exp is a neat trick that allows us to do that, even though, there's not an end to that sentence. Exp is a nice trick that allows us to do that. To avoid having to then keep unpacking and repacking this type, we fortunately get a type level monad with this reverse bind operator and pure specialized to exp. So to briefly go through this example, we've got not, null, filter, and flip, which are all defined by first class families and make this code significantly more readable. And because each one gives an exp k out, so for example, this filter, which checks each element of y's to see whether it's in x's, gives an exp k, and then we use this bind to unpack that and then apply it to null, same to apply it to not, and then eval the whole thing to get the result, which is a really lovely trick that's allowed for a lot of reusable code, and we'll hopefully show that properly in use in the next two examples. So now we can build our adjacency list and get one step closer to having this type level graph. I've grayed out most of the code because it's not super important, but the stuff that is important is colored and in bold and very, very clear, hopefully. So all we do is map this getAdjacent function to each node, and this just makes a key value pair, one of those mappings from earlier, from that node to all the nodes that satisfy the comparator and all of the nodes that satisfy the reverse of the comparator. So that's getting you all of the out edges, those that satisfy the comparator, and all of the in edges, those that satisfy the reverse of the comparator. We then implement depth first search on this type level adjacency list. Again, I've grayed out some of the code because there's a lot of code on here. Key points to mention are, we're just going to go through this key subroutine. Unbool is essentially if, but in reverse. So it's the false case, the true case, and then the condition, which makes sense purely because the reverse bind means that all of our code basically reads in reverse, which is a bit weird. But that's just something you get in exchange for all of the benefits that first-class families give you. So if we've not encountered a node yet, we're going to apply a search strategy to get a list of nodes. This is where our get in edges and get out edges functions from earlier from earlier apply. So instead of just having one DFS, we essentially have multiple DFSs based on how you explore the graph. So this could be getting all of the in edges or getting all the out edges or whatever, but we get them and then just apply DFS to each of those. And then because it's a post-order traversal, we're going to update the stack with the node that we were exploring in the first place, which is great. We now have this useful modular implementation. And we use this useful modular implementation to implement a bunch of cool graph algorithms that allow us to implement both both the topological sort and a couple of other bits from the paper. So topological sort is just applications of DFS get out edges, your regular standard DFS. Connected component search, which we use in the paper to find groups of computations that can be run concurrently, is just applications of DFS get edges, which are the undirected edges. And then finally, DFS on the graph transpose, which we use for Kosaraju's strongly connected component search, again in the paper, is just DFS with the in edges. So you get all of these algorithms at the type level for significantly cheaper than you would if you wrote them with normal type families and didn't have any of the modularity that we got. So with this, we're now one step closer to having our goal. We've successfully, what we have here is the ordered type family, which just combines the adjacency list building and the topological sort from earlier. We apply it to our comparator is less than, and that means that if we get in this list of computations of type x's, like we did at the start of this section, we can apply this type family to get a sorted version of that at compile time called x's prime. The final challenge we now need to talk about is getting the result of this topological sort, so getting a value of type x's prime, or h-list x's prime, sorry, back down to the value level. And that's what we're going to do in this final section. So we're going to, well, let's just get straight into it. When we have the result of a type level algorithm, there tends to be two possible approaches when reifying. First of all, if a type has a single associated value, you can just use that value. So for example, the unit type, good news, it's unit. Similarly, those type level strings we encountered, while they're not types, you can get a single value out of them. However, we're not working with types like that. We're working with this MIO reads writes A, which is slightly more complicated. There are many possible implementations. You can have if you just have like something that reads from X and writes to Y, you could just have something that reads it and directly writes that value. You could add one to it. You could do lots of different things. So we're unable to do that. The alternative is that you can re-implement this type level algorithm at the value level, which is not ideal. It means we're taking all the hard work we've done and having to repeat it. If we then went, oh, I want to change this analysis slightly, then yeah, bad news, you're going to have to rewrite it again at the value level, which is a serious pain. So what we propose is a little technique called rearrangement, which uses the values we started with to inform what values we get in the output. So here's the idea. We want a generic way to permute an input into an output. This is exactly what a sort does, right? We have a collection of values, and then we've sorted them into some new ordered collection, but they contain the same values. As such, what we assume is that the values of elements in the output are the same as those in the input, but reordered. So if we see an element of type int in the input, and actually that's meant to be somewhere else in the output, it'll still be the same int. So therefore, to reify an element of our output list, we're going to look up the first unused value of its type in the input list. So to give a very small example of what that actually means, let's say I've got this amazing list of type int bool unit, and I do some type level algorithm that goes, actually, this should be of type bool unit int. Then it's just a game of looking things up. We look up the first bool that we find, it's true. We look up the first unit we find, and we look up the first int we find, and we successfully get a rearrangement that successfully, or we've now got a value of the correct type, and we've done that sort at the compile time. So it's just a case of quickly doing this lookup at runtime to get this sort to be completed. And we apply this exact same idea to the larger computations that we made. A very brief bit about implementation. I'm only going to show the class here and not the instances. The instances are available in the paper and they're fully explained, and that's much more useful than me talking you through lines of code right now, especially looking at the time. So we implement this as a class rearrange_del, which takes in some input list type, and it gives us both the target list, which is like the type that you wanted out of it, and whatever elements were unused, which allows it to be used not just for sorts, but also for filters and other similar cases where the elements in the input should be the same as the elements of the output, or at least a subset of them. Now we can see this in use. With this rearrangement, we can now just say, okay, so we had this x's, and we did some type level sort to find an x's prime. We know how to rearrange these. So if we're able to produce a rearrangement for x's to x's prime, leaving no elements left unused, so it's a full permutation as opposed to like taking some elements, then we can just use this rdel function we just defined. And with that, we've successfully taken a problem with some dependency. We've successfully taken our computations, which have these read and write types. We've looked at the type level how to solve this, and then we've brought that back to the run level, to runtime. So, in conclusions, we used a graded monad to make the types of our computations, so those IO unit types that mutate state, more precise. So we now have these cool read and write types that effectively go, look, there we go, we can read and write now. We then used type-level programming to look for dependencies between those computations, and we used a dependency graph at the type level to order them such that the programmer doesn't have to worry about it at all. And then finally, we used these rearrangements to take the results of this type-level computation and bring it back to the value level for free. And with this, we can guarantee that our computations run in an order that satisfies those dependencies. And this is the cool new trick that we get. In the paper, there's some other fun stuff, like I mentioned earlier about running things concurrently. There's also some stuff about running partial updates, where if you know that a cell hasn't been updated, how many of your computations do you actually need to run? But for that, I recommend you check out the paper. So yeah, thank you very much.
All right, let's thank this. I will thank the speaker again. So we have 4 questions lined up. I'll take them to the stage one by one. Yeah, 4 questions.
Oh my goodness.
So the first question is by Chris Smith. I expected plus to subtract the first write set from the second read set, since there is no external data dependency when you read something you've just written. Would this be sound?
Supposed to subtract the first write set from the second read set. As in set subtraction.
Maybe I'll invite him to the stage, and then he can clarify a bit.
Yes, please. That'd be fantastic. Hello. Yes. Sorry for the confusion.
Yeah, no problem. I was just wondering. I expected, like, if I say, like, write to the screen and then immediately read directly back from it, and then I combine those 2 operations with a bind, I feel like I get an operation which should not necessarily depend on previous writes to the screen.
Oh, yeah, that's a really good. Yeah, I think that would be sound. So that would be, to confirm, you have some operation which reads from this. If you bound together the 2 computations in the robot example, do you mean?
Right.
I'm just going to bring it up just for clarity. So if you were to bind remove error and write to motor together, you would have dist to motor rather than dist screen to screen motor.
Well, I think you'd still need screen as a written.
Oh, yes, sorry.
Yes. Right.
I think it would still be sound. I would have to check. So that would be not reading from screen because you write to it. Yeah, I think that would be sound. I'm not going to make any sweeping statements at the end of a talk, but I think you're correct. That's a really good point. Thank you.
Great. I'll remove the invitee from the stage, and Mark has answered.
Fantastic.
And now I'm going to show the next question. What happens if the graph is cyclical?
Okay. Well, fortunately, we have
screen or write motor.
Yeah. We don't get an infinite recursion or a loop because we actively check for this. So in the paper, rather than just using topological sort, we actually use strongly connected component search and then check if any of the components are greater than size 1. Because if you have a component greater than size 1, you have a cycle. And as you said, if we didn't check for that, we would probably get some kind of infinite loop in GHC, which isn't ideal. So we actively error. There's some really nice error messages that say, hey, these computations of these types are all in a cycle. You should probably fix that. But yes, we've fortunately thought of that. That is a really good question, nonetheless.
Great. I'll mark that as answered. And there are 3 more questions. So Gergo Erdi says, the Chesco talk showed quite a lot of performance problems. What's your experience with GHC's type-level computation performance for these graph traversal algorithms?
That's a really good question, particularly because one of the reviewers brought this up and I didn't get time to properly investigate it. But from anecdotal evidence, from just compiling on my laptop, which is a fairly new laptop, it's like 16 gig RAM, something like that. We didn't get any memory overloads. We didn't test any particularly big graphs. I think the largest graph in the paper is something like 8 nodes and a collection of computations between them. So admittedly, it hasn't been like seriously tested like Chescal was. But from my experience, it was taking maybe 30 seconds on some of the worst compiles. So it really wasn't super bad, but proper investigation needs to be done. As I say, that's very, very anecdotal as opposed to formally tested.
Thanks. I'll mark that as answered. And then Dominic
Brilliant.
Orchard asks whether you can make a pull request for the rearrangements to the type level set package.
Yeah, sure.
Please.
That sounds really sensible. Yeah, I'll do that. I will screenshot that because otherwise I will forget.
Do that.
Whoop. Lovely. That sounds like good fun. I'll do
mark it as
that.
answered.
I really like that package, by the way. It's really clear and helpful. So thank you for that, Dominic.
And then a question by Andreas Klebinger. Have you thought about or tried staging as an alternative for compile time computations? I wonder if these kinds of type level computations is better or worse in terms of ergonomics, compile, and runtime.
Staging. What's staging here? As in, like, actually, yeah. If you could clarify, that'd be really useful. Sorry, I'm not too familiar.
I'll pull him in.
Brilliant.
You mean like template?
Oh, like
Haskell.
template Haskell. Oh, okay. Yes. We haven't thought about that. I was thinking about this morning, funnily enough, because that might be a way to avoid the rearrangement step by saying, oh, why do we do this rearrangement when we could just ask template Haskell to order it for us after we do a type level computation? So it hasn't been explored, but it's a good idea. And I think it'd be really cool to investigate. Sorry to pull you in when I realized what was going on.
No, that's fine. Well, I mean, I guess as a kind of follow-up, right? Just generally, when I did type-level programming, I didn't do a whole lot. But term-level programming in Haskell at least seems more ergonomic. And I imagine with template Haskell, you can just basically lift this up to compile time and just say, run this at compile time instead of having to reformulate it at the type level. And so, and you obviously, right, you went at the type level. So I wondered, like, I imagine there's a reason. I know there's cross-compilations issues and similar things like that with template Haskell. So maybe you have some ideas or opinions on when should you go to the type level instead of going towards staging?
Simply put, I don't. Like, the main reason I went for type level stuff is because it seemed like a sensible solution. I didn't really think of template Haskell when implementing this in the first place. I would really like to try it with template Haskell because, as you say, it would be much more ergonomic. A big part of why we use first-class families is to bring that type-level language closer to the value-level language by introducing partial type families, which give us all the higher-order functions that we really enjoy. So it would be really sensible to go and explore that because, as you say, it is much more ergonomic, and I don't know what it would lead to in terms of performance. It would probably lead to some nice runtime performance benefits because instead of having to perform this rearrangement, you would just sequence it like we did on the first slide, except guaranteed to be in the correct order. So I guess this is a nice case study for using graded monads with type level programming, but whether it is the absolute best approach, particularly for this example, I'm not too sure.
Okay, thank you.
Thank you. That's a really lovely question.
Kindly removing you from the stage, and then Mark, your question is answered. And the other one was, of course, answered as well. So I think this brings us to the end of the session. Thank you very much, Finbar, for giving the presentation and answering our questions. Well done.
Yep. Brilliant. Thank you. Oh, I can stop presenting now, can't I? And then probably get kicked off the stage.
And you get kicked off the stage.
Oh, no.